Hi, this is Dr. Jason Harrington, and today we'll be talking about initial value problems for ordinary differential equations. And we're going to focus primarily on numerical solutions and numerical approximations of them. So you don't have to have the ODE class or differential equations before this class. We're just going to be talking about the numerics. But before we get into that, definitions. So I'm going to give you the definition of Lipschitz and convex sets, the theorems that we're going to use to determine if a ODE has a unique solution, and then we'll lastly end with well-posed problems. What I'm going to have to do is give you some definitions on like Lipschitz conditions, convexity, and then some theorems that actually discuss what actually happens to make these things, or to make sure that we know that these ODEs have a unique solution. And then at the very end we'll talk about well-posed problems. So let's talk about an example. Now in most ordinary differential equations that you work with in physics, engineering, and in real applications, you have a nice, unique solution. So let's just do a very basic, a simple one from Calc 1. So in this case, what I'm going to do is I'm going to say the derivative of y with respect to x is equal to 2x, and I'm going to have this initial condition of y sub 1. When you put in 1, you should get 2. Again, this is a nice and easy Calc 1 problem. What you're going to do is you're going to just integrate both sides with respect to x, and you get y is equal to x squared plus c. You put in the initial value to figure out what the precise value of c is going to be, and then you have a unique solution to the differential equation. Now, the big question is when does the differential equation even have a solution? Does it even have something that actually works? And furthermore, is that solution unique? So here's an example of one that is not so nice. And again, you don't have to worry about solving these things exactly, because that's what you'll do in your ordinary differential equations class. But you have dy over dx is equal to x times y to the 1/2, or the square root of y. With the initial conditions, y sub 0 is equal to 0. Now you can see right off the bat that if y is equal to 0, so if I put 0 in there, you're going to get 0 on the right, and then the derivative of 0 is also 0. So that actually works, and we call that the trivial solution. And that's nice and continuous, and it satisfies all the conditions of the ODE. But there is another. So consider y is equal to 1/16 of x to the 4th. Now, what I'm going to do to check it, now this is what you have to do when I say check a solution for an ODE. First thing you're going to do is you're going to put on the left-hand side, and you say, okay, well, if I take the derivative with respect to x, I get 4 over 16 x cubed, which is really just 1/4 x cubed. And then I take the equation and I put it on the right-hand side. Again, I'm not solving the ODE, I'm just looking for, does it work? And on the right-hand side, I get x times the square root of y, so it's x times the square root of 1 over 16, x to the 4th. 1 over 16th is just 1/4. And the square root of x to the 4th is just x squared, and so x times x squared is x cubed. So there's at least two solutions, namely y is equal to 0 and y is equal to 1/16 x to the 4th. And that's not an ideal situation. And we'll talk about how do you recognize looking at the initial condition and the ODE to figure out if it even has a unique solution. Now, multiple solutions or no solutions is not very practical. And I have an example here, but I mean, imagine you're getting on a rocket, for example, and the engineer that designed the rocket said, well, there's two possible outcomes. One is it's going to go head first into the ground and explode, and the next one you'll end up on the moon, right? That's not going to make you feel very good. So scientists and most people that work with ODEs like to have unique solutions. Otherwise, the whole problem is not practical. Now, I'm a very visual person, and we talk about things like fluid flows and these other things. I like to imagine a model where you have a fluid and you simply drop dye into the water or the fluid, and you want to see where it goes. If the model has multiple solutions, so the initial value is going to be the drop of dye. So imagine this, water is flowing, you put a drop of dye. Now, in physics, we should know where does that drop of dye actually go. But if you have something with multiple solutions, then that drop of dye, you don't really have an idea. It could go just be straight, like y is equal to 0. It could oscillate. It could do all kinds of things. Now, granted, I find that fascinating, and I like that because that usually deals with chaos theory and initial value conditions, or sensitive value conditions. This model doesn't really help people who need a more precise model. So the first thing we're going to deal with is a function f of t, f of t comma y, so it's a multivariate function, it has two values, t and y, is said to satisfy a Lipschitz condition in the variable y. So we're saying that the y variable is the one that satisfies the Lipschitz condition for some set D that's a subset of the reals is a constant L greater than 0 that exists such that if you were to pick any two of these points, any two different y's, then it's going to be less than or equal to L times the absolute value of the distance between y1 and y2. Whenever that happens, when f of x and y1 and f of x, y2 are in D, the constant is called a Lipschitz constant. Okay? Now, for why that would work, notice here that if I go back to this is not a formal proof, but this is just an idea. If I take the two sides here, that's f of t comma y sub 1 minus f of t comma y sub 2, and I divide the whole thing through by y sub 1 minus y sub 2 less than or equal to L. If that's true for all t and t1, this almost looks like the derivative of f with respect to y. You see, so the theorem is not that far different. So for this example, let's go ahead and consider a function, we'll just call it f of t comma y, which is equal to t times the absolute value of y. And I'm going to say that that satisfies a Lipschitz condition. Condition on the interval, or on the set D, which is going to be equal to all the t comma y, such that 1 is less than or equal to t less than or equal to 2, and I'll just put that, and negative 3 is less than or equal to y less than or equal to 4. So you have to have Lipschitz on some sort of set, is what we're talking about. Now, what we'll notice is that for each pair point, for each points, I'm going to have t comma y sub 1 and t comma y sub 2 in D. We have the following thing. Let's just try it out. I'm going to have the absolute value of f of t comma y sub 1 minus f of t comma y sub 2. And if I just use the raw definition for that, I'm going to put that and that into the raw definition. That's just going to be t times the absolute value of y sub 1 minus t times the absolute value of y sub 2. Alright, now that, I can factor out both of the t's. So I'm going to have my t out front times, and now I'm going to have the absolute value of y sub 1 minus the absolute value of y sub 2. Alright, and that's going to be less than or equal to, and you'll notice right here, if I go back and look, that the t is bounded above at 2. So I'm going to use that to say that that's going to be less than or equal to 2, because that's what I'm going to use for that, times the absolute value of y sub 1 minus y sub 2. So, yes, it satisfies a Lipschitz condition, so f satisfies the Lipschitz condition on D, and my Lipschitz constant is L is equal to 2. And remember, this is my L. So basically, a function can be Lipschitz on a set. Now, you have to know what the set is, what the set D is, in order to determine whether or not it is in fact Lipschitz. Now the next thing we're going to talk about is convexity. We have a set D, which is a subset of the reals, is said to be convex if you take 2 points that belong to D. Then you have this point here, which belongs inside of D. Now, at first this looks kind of confusing. But what this says, now let me just play with this a little bit. You'll notice that if lambda is equal to 0, then I'm going to have the point 1 minus 0 times t1 plus 0 t2, comma 1 minus 0 y sub 1 plus lambda, which is 0 at that case, 0 times y sub 2. And you see that these terms go away, and I'm just left with the first set, just the first point, t1, comma y1. And then, if I say lambda is equal to 1, then I'm going to have 1 minus 1 t1 plus 1 times t2, comma 1 minus 1 y1 plus 1 times y sub 2. So in this case, what you see is that those two terms, the first point goes away, leaving you with just the second point. That's a 1 there, y sub 1. This will be y t2, comma y sub 2, which is pretty neat because that tells you that the first point you put in lambda is equal to 0, you get the first point, lambda is equal to 1, you get the second point. And what happens if lambda is between the two? Then it's a straight line between t1, comma y sub 1 and t sub 2, comma y sub 2. So it starts here when lambda is equal to 0, and then it ends up here when lambda is equal to 1. And what I'm saying is that when you construct these 2 points, any 2 points in the line, or any 2 points in D, and you connect them by a line, then they must exist in the set. So I'm a very visual person, so let me just give you an example so you can see it. So example, D is convex. If I have a picture like this is convex because any 2 points that I draw in there, no matter what 2 points I draw, they will be connected. Another one is if I have something like, say, a cone, maybe a ice cream cone. Let me make that top a little bit better. And again, I can pick any 2 points inside this ice cream cone, or maybe it looks like a pizza now, so I'm pretty excited. I should definitely not do this while I'm hungry. And you see that that's convex. Now, not convex, you're going to see things like, if I have a star here, for example, or just something with many points to it, and I draw a line that goes from here, or draw a point from here to here, notice that if I were to connect them, that's outside of D. So that little line right there is outside, outside of D. So that's what we mean by it's not convex. And there's a bunch of other little examples that one could give. If I had something like a big giant U, for example. And this has to be true for all points. So again, a lot of times students will miss the whole point of it, and they'll draw something like this and say, hey, that must be convex. But it has to be done for every single 2 points in there. So if I draw these 2 points, that's almost looking like a face now, but if I draw those 2 points, I connect it, now that's outside of D. So it's true for any 2 points. All right. Just to give you an idea. Now next, suppose that if f of t comma y is defined on a convex set, D is a subset of the reals again. If there's a constant L that exists such that the derivative of f with respect to y is less than L for all the values t and y inside of D, then f satisfies the Lipschitz condition on D in the variable with the Lipschitz constant L. Now, so you can see that if I take the derivative of f with respect to y and that whole thing is bounded, then we have the Lipschitz condition on f over D. So let me give you an example for that. All right. So let's try this out. Suppose I let D, the domain of my set, is going to be t comma y, such that t is between 0 and 1 and negative infinity, and so y is between negative infinity and infinity. And I'm going to consider the ODE that has something like, well, not even the ODE, let's just consider a function first. I'm going to have f of t comma y is equal to y minus t squared plus 1. So the first thing I'm going to do is I'm going to take the derivative of f with respect to y at the point t comma y, and I want to see if that's bounded above. Now if I take the derivative of this with respect to y, I just get 1. So that's going to be the absolute value of 1, which is equal to 1. So we see that f is Lipschitz with L equal to 1. And so it's actually pretty easy to do. The other thing too I want to note here is that for D, if I draw D out, I'm going to have my t-axis here and my y-axis here. And I'm going to go from, t goes from 0 to 1. And y goes from positive infinity all the way down to negative infinity. And there's something you want to note about that is that is in fact is convex. So we'll be using that later. Basically, if you have convexity with the fact that it's Lipschitz, will give us the fact that it's going to have a unique solution. So this is our existence and uniqueness theorem. That's the big hurrah of this actual section. So suppose that we have a set D, whatever shape that is. Now notice that with D, the way it's actually presented, A is between A, or T is between A and B, and lambda is, or sorry, Y, yeah, lambda's on the brain, but Y is between negative infinity and infinity. So what you see there is that it is in fact convex. So D is convex, and that f of t comma y is continuous on D, and if f satisfies the Lipschitz conditions on D in the variable y, then the initial value problem of y prime is equal to this function with these restrictions, and this is equal to some lambda, or sorry, some alpha, that will have a unique solution. So let me give you an example here. Alright, so for example, let's consider the ODE dy over dt is equal to 1 plus t times sine of ty, and we're on the interval from t is bounded between 0 and 2, and we're going to have some initial condition like y sub 0 is equal to 0. So y can be anything, so we're going to have y goes from negative infinity to, whoops, can't have equal to infinity, that's not a concept, negative infinity to infinity, and you'll notice this is going to be convex, because if I just draw a picture of it, again, I'm going to go from 0 to 2, and my y's can be any value there. So that's a convex set. Now my function, I'm going to set this whole thing to my f of t comma y. So my f of t comma y